All right. Let's see. What we're looking like. Okay. All right. So we're going to start off here. Single page. Okay. So let's see. I don't think this class is a little bit interesting. I don't think the next thing really applies to anyone here. Like, if you're on the call, that means it definitely doesn't apply to you. But like in some of my classes, basically what I did, I had to go through people that had like an excessive amount of unused absences. I submitted their name to be withdrawn. But the caveat was, I was like, okay, if you want to stay, they had to like contact me. I don't recall that really applying to anybody here. You guys were at least good at doing what I asked. So, at a minimum, getting your daily attendance credit. So I do commend you all for that. But if you have a friend or a classmate that got administratively withdrawn by the intent to stay, they need to contact me first via email. I need an email that has their first and last name with the M number, and then which course they're trying to stay in, along with the CRN. And I'll forward that to the registrar, and we can get them added back. Like I said, my memory, I don't remember anybody from this group that really pertaining to, but you might know somebody that falls into that category. It's not your responsibility, but, I'm just passing that on. And then, just, again, you guys were pretty good about, like, the whole point was this is remote asynchronous. So at a minimum, I need you guys to check in what you have been doing, at least. So that way you don't want to be in the boat of getting dropped and then trying to get added back, because if you just go too long without checking in, then you can get messed up, right? So I don't want anybody to not finish my class due to poor attendance, right? This is remote asynchronous, but I have you guys check in because we're required to take attendance. And so like periodically I'll have administrators come to me like, when was the last time you saw so-and-so? And so if we don't have any kind of way to check in and take attendance, then I'm not doing what I'm supposed to do. So that's why I have you guys check in. But again, all of this content is streamed. The full lectures are made available beforehand. So that's why I just found like it was easier to just do asynchronous, where if you need to leave for whatever reasons, it's okay. Just check in, get your attendance credit, and then pick it up when you're ready. And I just do the meetings live just to kind of simulate like if we were in person, but it's not really necessary. I just do it just because. Let me see. So some other pieces of information. Let me pull up the calendar really quickly. So that's going to be here. So we are at the top of week 13, right? We just had exam 3, right? We are rapidly approaching the end. So this week we're going to be working on section 3.1 exponential functions. Next week, I think we have section 6.1 or 6.4 further topics in algebra. It's going to be basically solving system of equations. That's the 14th and the 16th. So November 21st, which is a Monday, that's that Monday before Thanksgiving, we're going to meet. We'll probably start reviewing for the final at that point. That Wednesday, November 23rd, we more than likely won't meet because that's the Wednesday before Thanksgiving. We have Thanksgiving on the 24th and 25th, so enjoy your holiday. Try to enjoy your time with your loved ones as best you can, and just do what you need to do. And then after Thanksgiving, we come back. We're going to meet on that Monday and that Wednesday. I'm under the impression that Wednesday, November 30th, is the last day of class, and I'm under the impression that the reading period is that Thursday and Friday, December 1st and 2nd. So then after that, the final week is that first full week of December, which is December 5th through the 9th. Now, I went on to schedule your final exam. It should become available that Sunday, December 4th at 11 a.m. And you get like 5 full days to work on the final and put everything in order, right? So we're rapidly approaching that hard deadline of December 9th, that Friday, December 9th at 11:59 p.m. So what that means is that if you're trying to improve your overall grade, you want to go back and prioritize your exams, as they count for nearly 80% of your overall grade. You want to prioritize that. Once your exams are in order, the last thing you want to prioritize is the homework. The homework is going to be a whole bunch of work for little points, right? It's not no points, but it's minimal points. But once your exams are in order, that's the bulk of, missing points that you can recover, and you can earn up to 90%. You can also anticipate the final to be cumulative, so that means a little bit of everything from the beginning to the end, but it should follow the same format as the previous exams. Unlimited attempts, but there's no late penalty because it's due at the hard deadline, right? So, just make sure that your things in peers are in order. Also, just make sure to continue to get your daily attendance credit. That's important. You don't want to be in that boat of, you don't want to get booted due to attendance, because and that's money, right? And you just don't want to have to deal with that if you don't have to. Again, this class actually did do a good job of at least getting your attendance credit, which was the minimum that I've asked most people to do. And that's no small thing because everybody didn't do that. Some people are like clamoring, trying to get added back, right? So, I don't want you to feel like that's a small fee or anything. There was something else. Let me see if I can remember. Attendance, how to get added back, the final Thanksgiving break. We're rapidly approaching the end. Yeah, I can't think of anything else, right? Okay. So I'll check attendance again. I'll check Zoom at the 15-minute mark. So that's about 7.5 minutes from now. Okay. So let's take some time to go through this concept. So today we're working on one section in chapter 3, and we're going to be working on section 3.1, exponential functions. Okay. Let's see. So we have a few objectives. We'd like to define what do we mean by an exponential function. We like to graph exponential functions. We like to develop formulas for simple and compound interest. We like to understand the number e. And we like to graph the natural exponential function and model with exponential functions. Now, we're not going to have enough time to get through all of this together right now. Again, my pre-recorded lecture is available, so you could watch that. And the rhythm is about the same as if we were live. You just can't ask questions live, but the stuff that I would say is essentially there, right? But we'll do what we can together right now. And I actually do. I want to do a story time real quick. I did it with my previous group. This one. Seems like it's working okay. Okay. Let me see something. Let me check really quickly. Oops, that's not the right one. Let's see what they're looking like. Cool, look at these two. Okay. So to introduce exponential functions, I like to introduce it with this story of it's a story of the inventor of chess, the invention of chess, right? So again, I just went through my announcements. If you're just joining us, you have to watch the recording to just get the pertinent information. I'm not going to repeat that stuff. But for the invention of chess, there's the story of the guy who invented chess. So he developed the game and he presented it to the ruler, and the ruler reviewed the game and he was pleased with it. So he decided to give him a reward in his weight in gold, right? So the chess player, the inventor thought about the reward and he suggested a different reward. He suggested that on the first tile, you do 1 grain of wheat. On the second tile, you do 2 grains of wheat. On the third tile, you do 4, and then 8, and then 16, and then 32, 64, right? And so the inventor suggested basically to keep doubling the amount of grains of wheat until you get to the 64th tile, right? Because the chessboard is 8x8 tiles, so it has a total of 64. So the ruler thought about his proposition, and he agreed to it. He agreed to it, right? So instead of a reward in his weight of gold, he agreed to this suggestion. Let's just see how much wheat did the ruler agree to give the inventor. Okay, so on the first tile, I guess we'll call it N. On the first tile, he will put 1 grain of wheat. Okay. Let me see. And so this one is going to be So notice that 1 is the same as 2 to the power of 0. That's going to be 2 to the power of n minus 1, right? That's this. And then the total here, we have a total of one grain, right? And the total is going to be, I think it's going to be 2 to the power of n minus 1 like this, right? So that's the tile. So on tile, so when n is, let me kind of move this stuff around a little bit. So when n is 1, on the first tile, he did 1 grain of wheat, and he had a total of 1 grain, and that's going to be 2 to the power of 1 minus 1, okay? So now if we consider the second tile number 2, he's going to put what? 2 grains of wheat, which is the same as 2 to the power of 1, okay? And he has a total of 3 grains of wheat, which is going to be 2 squared minus 1, okay? On the third tile, if you double it, that's going to be 4, which is 2 squared. So notice that's n minus 1. And we have a total of 7, which is going to be 2 cubed minus 1. Let's do a couple more. On the fourth tile, he's going to do 8 grains of wheat, which is going to be 2 to the power of 3. And he has a total of 15 grains of wheat, which is going to be 2 to the power of 4 minus 1, right? The fifth tile, 16, 2 to the power of 4. And what is that, 31, which is 2 to the power of 5 minus 1, right? So again, the chessboard has a total of 64 tiles. That's not a 64. He has a total of 64 tiles. On the 64th tile, on that tile, he's going to put 2 to the power of 63 grains of wheat. And he's going to have a total of 2 to the power of 64 minus 1 total grains of wheat. Right? Let's see. So how much wheat is this really? Hey Siri, what's 2 to the power of 64 minus 1?
2 to the 64th power minus 1 is approximately 1.8446 times 10 to the 19th power.
1.8446 times 10 to the 19th power. So then we got to move the decimal 19 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There's 1,000, million, billion, trillion, quadrillion, 18 quintillion grains of wheat. All right. So when this story was first introduced to me, this amount of wheat would, I think the dimensions would fit just inside a silo. I think it was 25 miles by 25 miles by 1,000 feet high silo, something like that. Some really ridiculously large. Don't quote me on that last part. That's why I didn't write it. But this amount of wheat is much more wheat that exists that's ever existed even into the world today, right? So, the way the story goes now, somehow I heard this other part after the fact, like in some other setting. But supposedly the way the story goes is that when the ruler realized that he couldn't pay the guy, you know what he did, right? Supposedly he did off with his head, right? So that was that story, right? He did off with his head. But this was a demo on how quickly things can grow exponentially, right? So this is just a demo on exponential growth, which is what this section is about. Let me check on you guys in Zoom. Okay. Oh, I thought I let him in. He may have got put it. Okay. All right, so I'm gonna kind of let that ride for a moment. All right, so that story was, again, it was just a demo on how things can grow exponentially. Okay, so then that leads us into this discussion on exponential function. So we have a lot of terms and a lot of definitions, and again, everything that I'm going to say, it should be available in my pre-recorded lectures, so it's always available to you. So we have the exponential function, a function of this form, right? This guy right here, where a is positive and not equal to 1, is called an exponential function with base a and exponent x. and the domain is all reals, right? So when we were working examples before, we were working like what's called like a power function. So you had x squared, x cubed, x is some number, right? Those were like power functions. So now this is exponential function because our variable is now in the exponent. And so again, so we call this an exponential function as long as the base is strictly positive and not equal to 1, right? The general shape of an exponential function, if we start from the far left, it starts really, really like infinitesimally close to the x-axis. It passes through the point 0, 1, and then it grows like this, right? So this is an example. This is like the general shape of an exponential function where we have a horizontal asymptote, which is the x-axis. And so what that means is that in the long-term behavior, we get really, really close to the x-axis, but we don't touch it. So the graph of the exponential function is entirely above the x-axis. Okay. Notice that with this graph, every x is accounted for. Every x corresponds to another y, right? To exactly one y. If you think of any real number, you could find a corresponding y that would work for the exponential function. But notice also that the graph lies entirely above the x-axis, right? Okay. So we have more. It just keeps going. So let's kind of take a moment and do this example on evaluating exponential functions. Okay. So to evaluate, for instance, for part A, when x is 4, we're going to do f of 4. That's going to be what? 3 to the power of 4 minus 2, which is 3 squared, which is 9, right? So that result is 9. Copy. Okay. So then for part B, when x is negative 2. So then g of negative 2, that's going to be negative 2 times 10 to the power of negative 2, right? So a negative exponent causes the fraction to flip. So that 10 transforms to 1 over 10. So that becomes a negative 2 over 100, which is negative 0.02. Okay. Hopefully this makes sense. If anything is not clear, feel free to unmute yourself and ask questions. All right. All right, so for part C, we're considering h of negative 3 halves. Okay, so this is going to be 1 over 9 to the power of a negative 3 halves. So a negative exponent causes the fraction to flip. So this is really 9 to the power of 3 halves, right? So then when we have a fraction in our exponent, that's called a rational exponent. When we have rational exponents, that denominator of 2 is really the index of a radical, right? So when we divide by 2 in the exponent, that's really saying square root, right? So we can rewrite this as the square root of 9 to the power of 3. So then I think that result ends up being 27. And then for the final one, f of 3.2, that one I would encourage you to use your calculator. Okay. Okay, let me check on you guys in Zoom real quickly. Cool, yeah, yep, usual suspects. That is all good. As long as there's one, I will keep going. Ooh, okay. Conscious, let's see. So graph this exponential function, right? So if we were going to graph a guy like this, we can just like plot points, right? Choose several values. We would just choose these values of x, right? Just choose these values of x and then pass them through the function to find the corresponding y. I feel like this one is a little bit easier to start with. 3 to the power of 3 is 27. 3 squared is 9. 3 to the 1 is 3. Any real number other than 0 to the power of 0 is 1. So on and so on and so on, right? Negative exponent causes it to flip into a fraction, right? So then we get these ordered pairs. So then to get a sense of this graph, we basically plot these ordered pairs and we get an image like this. And then we connect the dots with a smooth curve like you see on the right. Okay. So this graph is typical for exponential functions when the base is larger than 1, right? So what we have on the left here, this is called exponential growth, right? As we go off to the far left, y tends to 0, gets really close to 0. Sometimes when you look at these graphs, it's going to look like it's actually touching the graph, but in reality, it's always space between our graph and the x-axis. As long as we haven't manipulated it, there's always space. It gets infinitesimally close going off to the left. Going off to the right, y tends to infinity, right? So with exponential functions, we have a horizontal asymptote, but no vertical asymptote. And then three key points when we're graphing exponentials is basically when x is -1, when x is 0, and when x is 1. Those three will rapidly give you the general shape or structure of your exponential, okay? So we have more. So we saw an example where the base a was larger than 1. And this one, we want to look at where the base a is between 0 and 1, right? Base a is between 0 and 1. Okay, and so same thing, if we want to look at this graph, we're just going to choose several values of x and then find the corresponding y. Right? So I feel like this one would be a little bit easier to do the -3 first. A negative exponent causes it to flip, so then it's just going to be 2 to the power of 3, which is 8. 2 squared is 4, right? And then yada, 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 right? So we have these ordered pairs, and then plot the points and connect them with a smooth curve, and we get something like this. So this one is called exponential decay. As we trace it left to right, it's steadily going down. It's monotone decreasing. As x goes to the far left, y tends to infinity. As x goes to the far right, y tends to 0. And notice that x still serves as a horizontal asymptote. Also notice that the domain of this guy is all reals. No matter what x you choose on the x-axis, you can find the corresponding y. But the range of this guy, because of that horizontal asymptote and just the nature of it, the range is the open interval from 0 to infinity. So it doesn't go below the x-axis unless you manipulate it, like you shift or you manipulate the function. Right? So the next 3 slides, we have some properties of exponential functions, or next couple of slides. Let me check here. Yeah, I don't know why it does that. It's been kind of acting up. I don't really know why. Until you guys just get my attention, that's just kind of how it is. Okay, let's try this again. Oh, optimize for video on? Oh, I didn't know that. That's the first time I noticed that, but share device audio. Oh, that's interesting. Okay, well, hopefully that'll help the video. Okay. So then we have these properties of exponential functions. Okay, so let f of x be an exponential function where the base is positive and not equal to 1. Then the domain of the exponential is all reals. Right? So that's what we said a moment ago. No matter what x you choose, you can find the corresponding y. The open interval 0 to infinity. So basically, the entire graph lies above the x-axis. Right? Since f of x plus 1 divided by f of x is going to be a to the power of x plus 1 divided by a to the power of x. But then we can break the numerator up into a to the x times a over a to the x. So then notice this is going to cancel this, and we're just left with a. So what this is saying is that the y value changed by a factor of a for each unit increase in x. Right? So every time we increase x by 1 unit, the y value increases by a factor of a. So when our a is strictly larger than 1, that's called the growth factor. It's going to be a, because each y value increases by a factor of a for each unit increase of x. F is going to be an increasing function. So when the base is larger than 1, f is an increasing function. So the graph rises as we trace it from the left to the right. As x goes off to the far right, y goes off to infinity. As x goes off to the far left, y tends to 0. All right, these are properties of the exponential growth, the regular exponential function. But now, when that base is between 0 and 1, we have exponential decay. and it's going to be a factor of a. In other words, y is going to decrease by a factor of a for each unit increase in x. Okay, so for the exponential decay function, f is going to be a decreasing function, which means as we trace it from the left to the right, it's going to steadily be going down the entire time. As x goes off to the far left, y goes to positive infinity. As x goes off to the far right, y tends to 0. Okay. Each exponential function is 1 to 1. Okay. So 1 to 1, that's talking about a function having an inverse, right? An inverse function is basically going to undo the original function. When we say a function is 1 to 1, that means every y corresponds to exactly 1x. An example of a function that is not 1 to 1 is a parabola, U-shaped curve, right? If you think about a parabola, each y corresponds to 2 different x's, right? So this is an example of something, even though it's a function, is not 1 to 1. This is an example of something where you could find a y that corresponds to more than 1x. So, but 1 to 1 means that every y corresponds to exactly 1x. So whenever you hear the following are equivalent. A function is 1 to 1. That's equivalent to every y corresponds to exactly 1x, but that's equivalent to the function has an inverse, but that's equivalent to, there's one more. The function, the graph passes the horizontal line test. So passing the horizontal line test, being 1 to 1, having an inverse, and every y corresponds to exactly 1x, all of those phrases can be used interchangeably. They all mean the exact same thing. Okay, so those are 4 different ways of that you might hear me say the same thing. Okay, and then algebraically, to show that a function is 1 to 1, if you choose, like, if you equate 2 different y values, then you can show that the x values have to be the same. But if this process going from here to here falls at any point, then the function is not 1 to 1. Okay. So again, if this is true, this is the same as f having an inverse, right? Okay, let's see what else. So he just keeps, I think this is the last of these properties. So then the graph of the exponential function has no x-intercept. Remember, we said it lies entirely above the x-axis, so it never crosses the x-axis. There's no value of x that will cause f of x, this exponential function, to equal 0, right? So we saw the exponential graph lies entirely above the x-axis. You're not going to find an x that's going to make y equal to 0 unless you shift, unless you manipulate the graph. The graph of f is a smooth, continuous curve, and it passes through these 3 key points, right? So when we're plotting, when we're looking at exponential functions, the 3 key points are basically when x is -1, when x is 0, and when x is 1. Those are 3 key points that'll give you the general shape of the exponential rapidly. From parts 4.3 and 5.3, we conclude that the x-axis is a horizontal asymptote for every exponential function of this form, right? So without manipulations, the x-axis serves as a horizontal asymptote. The graph y equals a to the negative x is the reflection about the y-axis of the graph of the exponential, right? So notice that we have a negative inside our basic function here. So multiplying the inside by a negative causes the, so instead of having exponential growth, this guy is going to have exponential decay, which we've seen already. Okay. All right, let me just check on you guys in Zoom. Hopefully that little change I made. Let me make sure it's the same person too, because I know some guys come late. Okay, I think we're good. Go away. All right. So I like to do another story time at this part. So before we get into like interest rates and things of that nature, I want to share this story. Let's go here. Okay. Can I get that to? No, that's okay. Come on. It's okay. There we go. Okay, so there's this story of this thing called the Infinite Scholarship. And so what this is basically when I was a student at Morehouse. I was attending an honor society like meeting, and this group got up to the front and they were like, hey, we're doing a fundraiser for this thing called the Infinite Scholarship, right? And I was like, Infinite Scholarship, what does that mean? So basically what it is that they had an interest-bearing account that was earning at least like 5% interest, and they were basically trying to raise funds to earn a principal of $1 million, right? So if you have, and this is piggybacking off of the lowest form of interest, which is called the simple interest formula, which is I equals PRT, right? So how much interest will that be in a year? If your principal is $1 million, right? And the interest earned on this account is 5% interest. So then the interest earned is going to be your PRT. So that's going to be the 1 million. I'm just going to abbreviate it as 1 million. No, let's just write it out. Let's not be lazy. So that's going to be 1 million times the rate. Now that 5%, we have to write it as a decimal. So that's going to be 0.05, and the time is 1 year. Okay. So then when you do this calculation, 1 million times 0.05, that ends up being $50,000 a year. That's full-time salary, right? So what this is saying is that if you had $1 million to deposit in an account and you had an interest-bearing account of 5%, that means that account would earn $50,000 a year. Hey Siri, what's 50,000 divided by 12?
50,000 divided by 12 is approximately 4,166.6666.
So that's about $4,000, a little over $4,000 a month, right? You don't think you can live? I mean, I guess if you got to the status of earning $1 million or acquiring $1 million, to set this up, but still, it's still interesting because I know people that have had that kind of money. I know people that have had that kind of money enough to donate it, to a school, to somebody else. So then I'm like, what would have been a better use of that would it be put it in an account like this that's earning interest. And so $50,000 a year ends up being like $4,000, approximately like $4,000 a month, right? Just them collecting, then you got to work out like taxes, but there are like maneuvers that you can do to legally like lessen the blow of taxes, like there's certain, I don't know those maneuvers, but that's what they were doing with the Infinite Scholarship. They were doing a fundraiser to earn $1 million. They had an interest-bearing account earning 5%, and with it being set up, as long as that account is active with those initial conditions, it would earn $4,000 a month, and that's the lowest form of interest. You can go higher. And so I like to share this because when you guys make your millions, if you're aware of compound interest, as long as you like with this setup, as long as you don't spend more than $4,000 a month, or in other words, as long as you only live off the interest, you have money coming in forever, as long as that account is active, right? So I like to share this story, so that I feel like somebody would hear it, become aware of it, and can actually use it. And so then you can start working towards generational wealth, right? And thinking beyond just the day-to-day, or thinking beyond just yourself. And like, okay, because obviously we can't take the stuff when we leave this body. We can't take any of the stuff with us. So then it's like, why would you hoard it so much? Why not, try to set it up to help somebody else? You know what I mean? I think it's a fantastic story. And these things exist. And there are other things that fringe on this. Like, even if you didn't have the $1 million, there are systems at work, at play, that kind of behave in this nature. Another example that I know some people do is like this thing called dividend stocks. And these are basically like, it's not truly like passive income, but it's essentially passive income. You would just need like a quality size like principal. But there are people that like, have a decent amount of money with like certain companies that have dividend stocks, and they basically give a return at the end of the year on money that you have on stock that you hold with that company. And it's basically what it is that the company's taking their earnings or their profits and divvying it out to their stockholders, right? So dividend stocks, and it's all over YouTube. I mean, you can check it, look for it, and I would definitely consult with like a financial advisor and see what you can create. But there's dividend stocks, and then another one where we have a person in our group. Their father left them this apartment complex, and this apartment complex generates like $20,000 a month. I mean, and it's managed by a property manager. So because they're the owners, they just collect the earnings, the revenue, and they go and live their life. I'm the type where I don't really believe in like trading time for money. I mean, I believe in it for some, but I know I personally don't want to do it, right? Because that's the lowest form of making money that we have. We all have the same 24 hours, but what is it that like one group is doing with their 24 hours versus another? Like the people that are wherever it is that we want to be, what are they doing with their 24 hours? And if we mimic them or emulate them in some fashion, maybe we can have similar results, right? So that's where like a mentor or a teacher or somebody like that will come into play. But yeah, when you trade your time for money, it's only 24 hours in a day, so you're limiting yourself. Even if you were making $100 an hour, and if you work all 24 hours, there's only so much that you can earn. So then the question is, well, how can you increase your value in the marketplace with the same 24 hours? We all have the same 24 hours. How is it that we can double our value with that same 24 hours, make twice as much or 4 times as much or whatever the number is, 10 times, 1,000 times, 1,000,000 times with the same 24 hours? And people do it. Right. So I just like to share those stories. I know it kind of eats up a lot of our time, but I don't mind doing that because, I do my pre-recordings for this. So all the information that I do want to share is already available. Right. So it's already there. I don't know if you guys are watching it or not, but it's there. So I feel like I did my part of at least making the information available and making myself available. You guys are intelligent. I let you guys, I treat you guys like adults. So I'll let you decide for yourself, and it's on you. I just try to cover my tracks and do what I'm supposed to do and just try to encourage you, right? I try to encourage you. Okay, I wanted to touch on a few more concepts. So we saw with the Infinite Scholarship a demo on simple interest. So I'm going to leave this. That's what this is here. I'm going to leave this as an exercise. I'm just going to leave this as an exercise for you. That's about right. Yeah, that looks good. There's one other part that I do want to talk about. We got about a solid 5 minutes. Okay. I'm going to leave that as an exercise. And then this introduced compound interest, where it's the interest paid on both the principal and the accrued or previously earned interest. But I'm going to skip this one because this is like this formula is if the interest is applied once per year. I want to get to the next one. So again, I'm going to leave this one as an exercise. But I do want to talk about this one, right? So this is the compound interest form. This is the one that we use most often. And there's like maybe one or two other interest formulas, like for annuities and things of that nature. But for our purposes, for right now, this is the main one I wanted to kind of chat about for a moment. So this is a compound interest formula. I would add this to my formula sheet. And this is if you have multiple compoundings per year. There's another one for continuous compounding. So again, I would encourage you to watch the videos to get the full shebang. But the A stands for the amount after T years. The principal is your starting amount. The interest rate, you have to express it as a decimal. So that's the interest rate on the account. N is your number of compoundings per year. So how many times you apply the interest per year. And T is your time in years. Usually the units for time are in years. And then, so this is the last one, and I'm going to leave this for you, but I want to give you a piece that you need for this. So if you were calculating the compound interest on this, we have $100 is deposited to a bank account that pays 5% annual interest. Find the future value A after 1 year if the interest is applied. So if the interest is applied annually, that means our N is 1. If it's semi-annually, that means our N is 2. Quarterly will be N is 4. Monthly N is 12, and daily N is 365. Right. So you would use these in the previous compound interest formula to generate the results. And then you should notice something with those outcomes. Okay. Are there any questions, right? I know we don't have a huge crowd, but one is bigger than none, so I'll go with it. If the let me go ahead and make this available. Okay. So when this bar finishes loading, you'll get a copy of anything that you saw me writing. And if there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. All right. Take care. Peace. Mr. Green Mac, are you still? Hopefully, you're still on the call.
Yes,
I see your chat. Let me see. It says use the 14 days. Did you ever pay for full access?
No, we just used the 14 days.
Has it already expired?
Yes.
What's his name?
Yeah, I'm not really sure because
What's his name? Did you say? Professor C. Oh, Professor C. I'm sorry. This is Malik's mom. My question is because I didn't understand it when we went to order his books for the class. For classes, it said he didn't need any books.
Yeah, because you have to purchase the full access to Pearson, so that's how we do our homework.
Okay, well, like he explained just now, I logged into I seen the 14 days, but I guess the 14 days is up at this point. Now,
yeah, I'm not sure because that's how I do the management. We don't meet. Everything is remote. There's nothing to print out. It's just submit the assignments there. I don't really know aside from that. And you have to log in through Blackboard. So maybe I would contact like the department chair, and if they can come up with something that's feasible, then that would be fine. Otherwise he might have to like purchase the full access and submit those late assignments because he can still earn up to 90%.
Okay, well, I mean, the only reason why I'm home right now is because I'm out of work sick, but I'm just trying to figure out financially how would this work, because I think when we went on there, it was like 100 and something, and then I seen that 14-day pass, and I was like, oh, at least you can hurry up and get some of the work done in the time being, and then if you need help with anything, you'll get in time, chance to ask him if need be.
Yeah. Yep.
But
yeah, aside from just purchasing the access and submitting assignments, I would contact the department chair to maybe he might have some like or the math office at Morehouse, and maybe they might have some other suggestion.
Okay, it's just so hard to get in contact with people. Already had like the not healthiest experience, and for him to be a freshman.
So with Morehouse, I would go in person. Like a lot of that, just go in person. Like that's part of the reason why I try to make myself available during class time, because it's difficult. It is kind of difficult. When I was a student, I just went in person, like whenever I could, because we didn't have the option for online. But whatever it was, I would just go there because it can be kind of a challenge to like reach people.
Okay, so I think for him, I'm praying that he gets a chance to pass all these classes that he's taking online, but this whole experience, I mean, for him, it's just been honestly not the best.
Yeah, it's tough. I don't want to be like it's any different in person, but they struggle even in person. Like in person, then you're just getting up and like physically being there, but you still gotta like, do things. Like you have to like, it's still tough. Like because like when we were meeting,
my bachelor's in health service management, and I know when I was in school, you have to be in people's face to actually get what you want. And to me, this is for him to be a first year student. This has not been, I mean, the best best for him, you know, because I mean,
Yeah.
I'm trying to be the greatest support for him overall, and he's trying his best. But like I've spoken to a couple of other former students that I've met through another organization that he used to attend,
Hmm.
and you know, they're trying to help us, but you know, they're graduates, they can only help but so far. And like I said, when I was on campus for intake
Hmm.
and orientation, you know, he has an IEP. Where is he going to get this extra assistance? And I told them then, the only way, I mean, financially, as a mom of three, I'm
Hmm.
not going to be able to afford for him to live off campus. And all I heard is, you know, not too much. And now he's doing online, and we're already after midterms, and he's still, you know,
Yeah.
struggling with some of the stuff. And this is not fair when you're
Yeah.
paying so much money into this. So
Yeah.
I'll
Yeah.
I'll go ahead and let him go ahead and email whoever he can. I'll figure out how we can do it so he can get this done. And I'll have him reach out to you periodically when he's on there to,
Hmm.
like, if he needs extra assistance with anything, try to, you know, just tell him to speak to you. But I just, like I said, you know, just bear with him because it's not easy. It really isn't easy,
Yeah.
financially as well. So I'm just,
Like, I personally don't have access to like funds or stuff like that. Like, that's why I was like, well, starting with the math department, that's a good place. Now, it's just tough because like there is a technique where, you know, he could sign up for the 14 days, but it would have to be like literally the last two. Like, I had one or two students in the past that were in a similar boat, and it's a gamble, but they did it, where they essentially waited until there's like 2 weeks left, and then they sign up for the free thing and submitted it all that way. Um, I had one student that tried that. It did kind of get a little bit turned upside down, but I mean, there are people that do that, and they were able to keep moving. Like, it didn't stop them.
okay.
But that's one technique. But again, I was trying to get something that's like more official or something, so you don't have to do all of that. Because waiting to the last minute, and like their claim was that they were practicing all the while, you know, but you know,
But
that,
the 14, the trial for the 14 is only a one-time thing, right?
yeah, it is just a one-time thing. So it's like, you know, we would have to like, I mean, you would have to kind of do something, you know, like he had to sign up for it separately. Like, if he can access the course ID, I think he might be able to sign up. I don't know. But I think the best thing is just start with the math office and see if they have any like suggestions or solutions, and then from there we can. Because what if we can come up with something that's feasible to get them through? You know, I'm open to it. We just have to figure something out that will work.
Okay, sir.
Yeah.
Thank you.
Mhm.
All right. Tell him.
Thank you.
Yeah. Take care.
You too.